First and foremost, a huge shout out to our amazing team of volunteers for putting this series together. We would not have this series without them. All of them are present as panelists on this webinar. Feel free to reach out to us with any question you have for this session. I, Joseph Itopa, will be the speaker, and all other leaders will be present on chat to support you. Feel free to reach out to us with any questions you have. Secondly, we would like to thank our sponsor, Home Depot, for putting together much needed events for our community. Do show your appreciation for them by retweeting our post. Helena will be sharing them on the chat, or Sumano will be in charge of that. We are in week 5 of the series, and here is what we have in store for the upcoming session. It is a single registration link for all the sessions. So if you are on this webinar, you have registered for all the sessions. Thank you for that. A round of housekeeping before we start. You can download the slide for today's session at this URL. One of our panelists will share this information in the chat. Feel free to download the following along. If you have any, feel free to download and follow along. If you have any questions regarding today's session, post them in the Q&A box so that one of our experienced panelists can answer them during the session. If you are facing any issues during the webinar, do chat directly with the panelists so one of us can help you out. Finally, don't forget to follow us on LinkedIn and join our Slack channel. One of our panelists will share this information in the chat section. So today we'll be covering time series data. And we are going to talk about time series data, categories of time series data, different time series data.
Joseph, sorry to interrupt. Can you switch the slides and go to presentation mode? You still seem to be on the first slide.
Oh, sorry about that.
Thank you.
Oh, okay. Okay. I hope the screen is okay now.
It's perfect. Thank you so much.
Oh, you're welcome. All right, we'll be talking about time series data, categories of time series data, different time series, types of DTS, and of course we'll discuss seasonality in time series, type of seasonality, trend in time series, which are very, very important, and type of trend. And we'll also talk about feature engineering in time series data. Then we round it up with time series forecasting, which is the heart of the whole discussion. So, time series. What is time series? From my observation or from my experience about time series, when things occur and it is recorded with respect to time, we can put it under time series data. We can call it time series data. And basically what it is observations that occur over time is regarded as time series data. So it may look a bit awkward to understand. Of course, let's say for instance, you have a family and you decide to record the date of birth of each person. So each person is an observation and their date of birth is what makes the observation time series data. It's that simple to understand. Taking a look at the image by the right of your screen, you will see the signal plots, and they are plotted based or with respect to the years you see on the chart. So each observation is taken based on the time, and this makes it what a time series data. So we are going to take a deeper look at this. Well, the point we are basically saying is that time series data is data collected based on time, with respect to time. So it's not difficult. Then we have two categories. We have stationary and non-stationary. And when we are building a model, a forecasting model for prediction, one of the easiest way of going around it is first to carry out some tests to decide or to be able to know whether the data is stationary or non-stationary. It must belong to one of the two categories. So being able to identify the category the time series data fall into helps us to know the best approach while building a model. So we are going to look at these two options here. So we'll talk about the stationary time series, and basically what it is that it is a time series that has neither trend or seasonal effect. And when you are saying trend, what do we mean by that? We are simply saying that, okay, you have a signal that is neither decreasing over a long period of time, or increasing over a long period of time. Like what you see here on the chart on figure 2a, you see that the signal is quite stable. You may say, oh, this doesn't look friendly. How is it stable? If you consider the amplitude between 20 and 30, you'll find a mean around 40. And once you have a consistent mean and variance, such data is classified under stationary time series. So, and you can also see the signal that is kind of consistent along the path. It's neither increasing nor decreasing. So it is a stationary time series. Now, to model time series, the time series must be stationary. Why? For effective modeling. We'll talk more about that and how we can fix that, because when our model seems to be non-stationary, it will be difficult for us to handle it, but we'll look at that as we move ahead. Then the non-stationary time series, which is obviously the explanation I'm trying to give, you can see that there is an increase. It keeps increasing. The trend seems to be increasing. Such is regarded as what? Non-stationary. And you can't get a mean for this. The variance is not consistent. The mean is not consistent. So it is what? A non-stationary time series. So, and one of the major characteristics of non-stationary time series is what? Seasonality and trend. Well, I have explained trend to mean that a trend exists when there is a long-term decrease or increase in the data, the decreasing or increasing value in the series. So as we can see, this is increasing. So this is a trend. This is one of the features of a non-stationary time series. And other technical part that we are not also taking into consideration, which I mentioned earlier, is the mean and the variance, which are what's not consistent. And lastly, we did not tend to see some kind of seasonalities being present. So when we are saying seasonality, we basically meant that the repetitive short time cycle in the series, you have the data, as the chart shows or indicates, you have it repeating itself over a short period of time, and at every interval that the data is recorded, it keeps repeating itself. So that is seasonality. We'll get into that. So here we have another example just to clear the doubts in our mind. You can see this is a stationary time series, and this is a non-stationary time series. Why? Because you can see the decreasing nature of the signal, and at a point it starts increasing. So it doesn't maintain a consistent mean or variance as it moves over time. But on the stationary time series, even though it seems to be a collection of, it looks like a stochastic process. One thing that is constant is that it is not increasing, neither is it decreasing. Such makes it what? Stationary. And if we take the mean around the amplitude, you realize that you have a consistent mean around the amplitude and variance. So let's go to the next one. Okay. We have stationary processes and stationary model. So we talk a lot about stationary time series. The reason is because whatever model we intend to build concerning forecasting or prediction has a lot to do with what? Stationary time series. So even if our data is not in stationary, it's not a stationary time series, we most likely have to convert it or transform it into stationary time series data before we can take it from there. So we have a stationary process. It's a process that produces a series of stationary observation. It's a phenomenon. You just have to put into observation that, okay, as we collect these data points, we collect them at a particular interval, and we ensure that the data we are collecting is between a certain mean or variance. So this you see here is an example of that. So the process of doing that, or the phenomenon to describe what is happening, is stationary process. Likewise, we have the stationary model. It's a description of a stationary series of observation by a model. We build a model, and the intention of building a forecasting model is not just to get a prediction and start dancing around it and be like, okay, it's wonderful. We intend to, at a point, to be able to have a model that fits the data points. And this model cannot just do that without a stationary data and time series data. So after transforming our our raw data into time series data, the model that tends to fit that data is what? A stationary model. So we talk about trend stationary. It's a time series that possesses no trends. And it may look somehow, you may be like, okay, that is not what you expect, because you can't call something trend stationary and the definition seems to go against the title, but that's not the case here. You have to look at this example, this chart we have here. You can see that there's no trend in this. It's neither increasing nor decreasing over a long period of time. So we can't say that it has the feature of maintaining trend. So such is regarded as what? Trend stationary. Then we also have seasonal stationary. This does not acknowledge seasonality, and we have explained earlier that seasonality is what? The repetitive short time cycle in a series. You have a signal that has a nature or an attribute of repeating itself, a particular action over a short period of time, and after a while it does it again. So here we have no such occurrence, so we cannot classify seasonal stationary to be what? To have the characteristics of seasonality. So we'll talk about DTS and why do we need DTS. It's very important. I may have mentioned it earlier, but I do not know if you understand it, but I'm going to explain it. The essence of what? Differencing time series data. We want to build something nice. We want to build a model that can do something great, that can have a high accuracy. So, and we can't do that by just ignoring some steps, because at the point, the trends, the seasonality may act as noise in the data set, and noise can be in form of an outlier as discussed in our previous series, and such can hinder the performance of our model. So we have to take time and look at the differencing. So differencing is a method for transforming time series data. And we said, why differencing? Of course, we see that the essence of doing that is to improve the performance of the model. So here, what you have already, I believe you are familiar with this. This is an example of a trend. And you can see the data points. They occur at different time, and they kept increasing based on the signal plot you are seeing. And this means that you don't have a consistent mean or variance along the y-axis. Same when you come over here and you decide to take a look at this. There seems to be an improvement after transformation, though it's not a significant improvement because you can still see some of the the signal is actually on an increasing path, and so it makes it difficult for us to handle, but it is better than what you see on the left. That is for the first figure you see here. So let's take a look at one more terms we need to understand. So when we are saying differencing, we shouldn't look at it like a very difficult stuff or something very complicated. Here is an example. Differencing, we can maybe take the method or technique of lag differencing. The essence of that, looking at this equation, is just taking the current observation and subtracting the previous observation from it, and that gives us the differencing. So we don't have issue. And that's basically what lag differencing does. And we can have lag 1, lag 2, and lag 3. And what those basically mean is when you take the first lag difference, for instance, this occurs at 30, let's say seconds, 30 seconds. And the occurrence of this particular observation takes place at around 35. If you take the present one, which is 35, and you subtract 30 from it, you have the difference, which is 5. And in such a situation, the current the current lag you took, which is this, because this is the origin, and it occurs along the x-axis. So the current part you took, which is this, actually gives you the lag 1, and the previous one gives you lag 2. So it's not really difficult. But then if you have multiple of those, what you get is difference order. You can have difference order is basically the number of times that differencing is performed. So you can have it performed multiple times. Like here we have lag 1. The moment you start having lag 2 and lag 3, that is what is meant by the difference order. So, and we can handle this manually through our Python code, or we can also do it automatically using pandas diff method. This method actually helps us to achieve this easily. And you may still be wondering, do we need all these things we've been talking about? How do they correlate? We need to take more look at it. What is happening? Too many terms to be described. But the truth is you need to understand the basics, and the basics depend on those terms. So that is why you see us discussing this. Already you can see the signal. You can say if it is a stationary or non-stationary time series, and then you can be able to observe further and said, okay, can we take the lag? Can we take the lag and understand how this, and transform the data into a particular form that we can use? So that is that. So we'll talk about seasonality. And when we do this, we've talked about trend and we've talked about seasonality. Those are the two characteristics of what non-stationary time series. And whenever we want to convert our data set from non-stationary to stationary, or we want to transform them, we have to deal with seasonality and trend. They are very important. And why are we doing that? Because we want our model to perform better. So we are going to consider type of seasonalities. I have described seasonality earlier, and I have made it very, very descriptive, but I am still going to talk about it one more time before we talk about type of seasonality. Repetitive short time cycle in a series is regarded as seasonality. When you have an occurrence happening over time, maybe I'll find an example to show you what I meant, but let's keep moving forward. So, example of all type of seasonalities. The first one is time of the day, and here you have a chart with data points collected every hour of the day. So this is an example of time of day seasonality, and you can have it in a situation like this. We cannot just go ahead. Visualizing it won't be a problem, it's wonderful, but building a model with it, forecasting, it becomes a problem. We have to transform it. And while doing the transform, it makes it easy for we to use supervised learning algorithms to train to actually fit the data set, basically, to fit the data set. So let's take a look at one other stuff here, which is the daily. For the daily data set, those are data points collected every day. You can see the x-axis time of the day. You have the first day, the second day, the third, all through. Do not be confused by the even numbers you are seeing all through. Before it, you have the 1, and at the middle, you have 3, and so on and so forth. So what we are just simply saying is that, okay, those data points were collected each day. So it's just like when you decide to download the historical temperature data set of a particular location in the world. You can download the data per hour. You can the temperature data for per hour. You can download the temperature data for per day or average monthly average. You can get it that way. So in this case, what we have is per day, each day, I think till the 30th day. So we can also consider the weekly observation. As you can see, the dates on the x-axis indicates when the data were collected. They were weekly data collected and plotted. This is a data of active users, weekly active users, and you just have to plot the visualization. It looks beautiful during the visualization and wonderful. Where the problem comes in is by the time you decide to build a model with it, you start having issues. So this is just a type of seasonality, and it's good we understand it, and for we to know how to handle the problem. Then, so we have the monthly, which is also type of seasonality. Those are data collected per month, number of monthly active Instagram users. So I think it looks a little bit different from when you're collecting daily and weekly. So it's kind of, it is easy, but here is one thing you need to understand. When we have this in our data sets, we start thinking, should we carry out feature engineering, or should we index the seasonality? So we are going to take a look at that quite right. And then you also have another type of seasonality is yearly seasonality, where we are simply saying, okay, data collected per year, like energy consumption. So it could be oil, it could be code, it could be anything rather. Let me be sincere with you, but we are just saying, okay, at the end of an entire year, what was consumed or what was utilized. So over several years, we plot and visualize and see if there's a trend or seasonalities happening. And in this case, this is seasonality. Just as explained earlier, that it's something that occur over a short cycle in the series. So we just know that every year there must be energy consumption, and every year we have to record that. And when we record that, we have it presented or visualized. So such repetitive observations is seasonality. So okay, we'll have a simple quiz just to get us going. Select those that are type of seasonality: daily, weekly, globally, yearly, trend. Drop your answer in the chat section just to keep us going. Feel free to drop your answer, be it wrong or good answer. Don't feel bad about it. The worst that could happen is you learn from other person's answer. So just drop your answer while we keep going, at least to keep us engaged, because the good part of it, we are so close to it. Yeah, we should have fun there. So trends. Types of trend. Already we talked about trend and said trend is an increasing or decreasing observation over time. Those we have agreed that they are the two major characteristics of what non-stationary data, time series data. In this case, you can see that this is increasing. And for an increasing signal of this type, it is difficult for you to get what the mean of the amplitude or the variance. It will not be consistent. It keeps changing. So in that case, it is under non-stationary. But then we still have more things to talk about, which is deterministic trend, which is the type of trend. The trends that are consistently increasing or decreasing are regarded as what deterministic trends. And then we have stochastic trend. This is trend that are increasing and decreasing inconsistently. Stochastic trend are actually giving birth to from stochastic processes. Stochastic trend are occurrence of random processes. What we are simply saying is that when they say stochastic, it's not a big word. We are just saying, okay, random occurrence or observations. So the more they kept occurring, the more data points we have. However, the more we realize that we cannot have a consistent mean or variance for the data. So that is regarded as stochastic trend. And if you compare it to what you see earlier, this is more consistent, even though it was increasing. Whether it's increasing or decreasing, it seems more consistent, but not on the amplitude compared to what you have here. So, and this seems to be more, will I say, it's also a type of non-stationary plot, but there's a difference, obviously, and the difference lies in what we are talking about. You can see a chart below here. Okay, I think this is the chart I was somehow looking for. So we can see a chart here, and this chart, the blue line indicates a stochastic trend. You can see it is increasing but not consistent, and the red line seems to be consistent as it is increasing. So they are both non-stationary, but there is a difference between the two of them. So let's take a look at the next type, which is the global trend. Okay, sorry, my mouse seems to be misbehaving. I don't know why. So for a global trend, we are basically saying, okay, the trend applies to the entire time series. So we regard that as what? A global trend. Meanwhile, for a local trend, it happens at a particular period in the observation. Such is regarded as what? Local trend. So they are not, as you can see, okay, you can see that there's an occurrence here and it's quite consistent, but that's not what you have along this path. So what you have here seems to be different from what you have there and there. So such is a local trend for you. Unlike on the global trend, where you have it consistent or happening to the whole time series, to the entire time series. That is the difference between global trend and local trends. So we'll talk now about feature engineering. Okay. We already know that feature engineering in machine learning or in data science is actually generating a new feature from an existing feature. Imagine you have a column of data set and you just, based on the data points or the data on the column, maybe the data is a kind of ordinal or categorical. We'll talk about that. And you just decide to create a new feature out of that feature. That is feature engineering or feature selection. So, okay, we have to take time and look into this and understand whether feature engineering, is it a friend or a foe? First, when we are looking at data, data can be categorical or numerical in nature. As we, as data scientists, decide to kind of annotate it. So they can either be categorical or numerical. Then for the categorical, it can either be nominal or ordinal. And all those terms look like, wow, such a time, I don't even know what they're talking about. But then we'll take a look at those terms because they will help us to understand whether we need feature engineering or not, and how do we need it. And then we'll now take a look at how it has impact on time series data. If you look at the image by the right side of your screen, you'll see that you can have some, looking at the word class, you see you have state gov, you have private, self-employed not included. So you have those happening and you have some repeating themselves. And if you come to the gender feature here, you have male, you have female. So by looking at this, we are concerned, how do we make sense out of this data? And our model can only be trained with numbers, not this. So we start thinking, how do we handle it? And when we have that thought, it takes us to the point of saying, okay, let us introduce feature selection or feature engineering. Meaning, why can't we just create a column, create a new column and said, okay, this column is for gender male, and we just have male fill the column. Or we can create another column and just say gender female and fill it with female, and call it female column and fill it with all the female data points. By doing this, we can now convert them into numbers and say, okay, 1 for male, 2 for female. So we can pass that to our model, and our model will be like, okay, I think I understand this you're sending to me. But in a situation where you have something different, it becomes difficult. You have no letters. Of course, your model will throw an error and be like, okay, I don't understand letters, I don't understand words, I need numbers. So here is another example describing feature engineering. We can, let me keep this here, okay. So nominal categorical data, which is one of what we are having here, categorical that could further be classified into either nominal or ordinal. Ordinal are in order. You have low, medium, high, you have agree, neutral, disagree, you have them properly arranged, and you know that they are in different classes. But when you have nominal, yes, you know, for instance, you see Toyota, Benz, Tesla, Mazda, they are all type of cars, car producers or car manufacturers, but they are not in order like this. You cannot say Benz is high and Toyota is low, so which is what you can do under ordinal. Here you can't do that. You can only have the classes of those data, and then you assign numbers to them. On in ordinal, the situation becomes a bit different. What you have is a category of either low, high, medium, agree, neutral, disagree, something like that. So you can then assign numbers to them. Like before I take it further, you can have low, medium, high. You can introduce another type of data in between, like something else I don't know, but it's a bit difficult. Unlike here, where you can introduce another manufacturer, you can introduce another type of maybe pen, pencil, eraser. You can introduce something else to add to that. Junior, senior, expert, professional, or amateur. You can add something else to that. It's not that easy on ordinal. Ordinal seems to be fixed, except you decide to introduce something different into it. So let's take a look at this brief example, and you will understand where it is taking us to. So when you take a look at categorical feature here, this is an example, and you have socks, fox, socks, box, things like that, and you have integer representing each of these. And then you said, okay, we want to feed this to our model. What do? You decide to take a step further and apply one-hot encoding, because one of the way to handle categorical variables is what? Encoding them. So when you say encoding, we are basically representing those data or categorical data, we are representing them with numbers. And we want to make sure that we are not just representing them with numbers that when you see one at a particular place, it changes at the other. No, we want to make sure that throughout the entire data set, whatever is being represented, for instance, if Toyota is 1, under this nominal categorical data, if Toyota is 1, throughout the entire data set, Toyota will be 1. If Tesla is 2, throughout the entire data set, Tesla will be 2. Not that Tesla will be 1 at the beginning of the data set, and towards the end you have 3 as the encoding value. No, it's not like that. So here we use one-hot encoding to encode this. And what we did, okay, we first come here and said, okay, government employee, private employee, and the like. Oh, I think an example might have been skipped. Let me describe it properly. Okay, you have figure 18a. You have this categorical feature, integer feature, or the value. So you decide to encode it using one-hot encoding. And what you did there was simply to take the integer feature, and each of those variables or data that you have, you call it, you decide to give it a title and call it a new feature on its own, like categorical feature socks, which is what you have here. And then you say categorical feature fox, which is what you have here. So having created these new columns, the next thing you do is that, okay, for the integer feature, which is what you have here, you want to say, okay, for the categorical feature fox, where does it occur? You come here, you pick 1. So you're using 1 to represent the occurrence of what? That particular integer feature. And then when you come to this categorical feature fox occur at the second spot. So you represent it as 1. So, and like that to the third part where socks appear twice. So it will be 1 and 1, but for different columns. Now, this is a very good way of handling variables of this type. The only problem we have is if we have many of these categorical feature here, it becomes issue for us. We'll have many columns. And when we have many columns, it may start introducing kind of noise into our model. So our model may start misbehaving. So it's only efficient or effective for when you have few categorical features like we did here. Then we can also follow the same method to encode the type of employees and create new column for each type of employee, and then we represent them with one wherever they occur. So this is feature engineering. We are just creating new features from existing feature. So that's basically all there is to that. And we'll now think about how do we employ this in time series data, because it seems like we have been way off. So to do that, we have to take a good look at our time series data. First, we have time features. And one of the things you need to understand is the date time. The date time can be splitted or can be used to create a new feature, such as in this case, in figure 19, you can see we decide to pick the hour. We have the 0 hour here, 1, 2, 3, and 4. So we decide to bring out the hour. The minutes is 0 or true. So we left it at 0. So that what we've learned from the other side is what we are doing here is simply encoding the data, or in this case, we are not encoding, we are creating a new feature from an existing feature. So there are two ways of going about feature engineering. It's either you encode the data and use it to create a new feature, or you just go ahead and split the feature to create a new feature. That's the present feature you had. Just like in this example we have here, we have the date time and we decide to split it and possibly drop the year, the month, the day, and just pick the hour. That is what we are interested in. So you can also have this for, this is another example here, okay? Daytime features are relevant in forecasting if used properly. It can be used to generate some new sets of features such as year, week, etc. You can see what we have here. This is the date time we had, and we just applied feature engineering using this previous feature to create a new feature, which is year, month, day, and for number of week, of course, we are the one that personally introduced that. But for this particular feature you have here, these are the three features: the year, the month, and the day that we make out of that. So this makes you to wonder, why will we do all this? Because we intend to build a model. We intend to build a forecasting model. And why all the feature engineering? Why can't we just go, if we decide to build this model, won't it be a problem if the year is different, the month is different, the day is different? But no, it's not like that. Because by the time you build the model and you want to run a prediction and your model is asking you, okay,
Hey everyone. Seems like something's up and Joseph seems to have gone off the call. Um, do wait for like a few minutes while we figure this out and have it up and running. Sorry for the technical difficulties.
Hello. Okay, hello everyone. I am so sorry about what happened. I thought I was actually charging my internet device. I didn't know I wasn't. That was why it went off. So I'm so sorry. I owe you guys what can I owe you guys? I don't know. An apology rather. Sorry about that. Okay. So um let me round up on time. Um So that is that about feature daytime features. We've talked about time features, we've talked about date features, and of course we talked about lagging in data. So lag features are variables or features that lag behind other features, thus making it difficult to predict. So we talked about this earlier, and we said when you take the previous observation and subtract it from the current observation, you get your lag. So, and when we do that, how do we handle it? Because we can have multiple lag, which we regarded as what? Difference order. So it becomes difficult for us to handle such. Uh, Once again, my apologies because, okay, that's that for that. So um, that is all about lag features. We can have the previous observation subtracted from the current observation, and we call it a lag. And when we have multiple of those, we regard it as difference order. So, and sometimes it may be difficult to predict when we have such. So selecting and predicting relevant features requires identifying and isolating lag features. So using a method regarded as what recursive feature selection technique. And you may be saying, okay, we have introduced a new word, Joseph, this is not fair. Okay, here is what recursive feature selection technique is all about. It helps us to feed the model by removing the weakest features until the specified number of features are reached. So recursive feature selection technique is actually a feature selection algorithm. So it's still under feature engineering. We are just trying to generate something, generate a new feature by taking a look at the lags that we have in the data sets. So we talked about something else.
Hey Joseph, sorry to interrupt.
Yeah.
Can you move it to presentation mode, please? There are a couple of participants requesting that.
Oh, okay. I'm so sorry, guys. I just don't know. Okay. Oh, I didn't know my Zoom was still on the previous this thing. Okay, here's what I was talking about. Sorry about that, guys. If this would have been a physical meeting, I would have owe you guys maybe something what using apologizing. So when I'm talking about lag features at this stage, we've looked at features, looked at date features, and here we're talking about the lag. To remove the selection is a feature selection algorithm. Basically, that's what it is. And when we say lag features, what we are basically doing is that we are creating a new feature that we regarded as lag feature that is generated by taking or subtracting the previous observation from the current observation. The result of that is the lag feature we are talking about to be recorded under the lag features. So I hope this is very basic to understand. Sorry about the errors I have put in this evening. I don't know why. So here is the last part of it, which is the window features. The window features seems to be very LIC friendly because it looks fancy with this image here. What we are basically doing is that we can take a certain interval, like in this case, the first image you're seeing, figure 22, takes 7 interval, and those interval is regarded as window. But in this example, we take 2 intervals, and all we basically do is to pick the previous value for the current, for the new feature we've created. Here, we cannot do that, so we put a none. There, we cannot do that yet, we still put a none. So when we decide to pick feature, what we do is that, okay, after that observation, okay, after that observation, you have this. So to create the third data here, we have to pick the last previous feature. In this case, we are considering 2 windows. So we keep replicating it till we have all the data we are concerned about. And in most cases, of course, it's an average. So we are not really saying, okay, this should represent that. So we have to take the average and say, okay, when we add these together and divide it by the number of occurrences, what will we get? But in this case, as it moves forward, we have to be cautious of the point the window is. I think another example that is self-descriptive is the expanded rolling average, which is still under the window features. So what we are doing is that, okay, in this case, we are also taking, window of 2. So the first one, we can't regard it. So we plus 2, we have 5. For the third one, we leave this and we pick, sorry, I mean, we add the 3 together. So as the window keeps moving through this animation, you can see that as the window keeps expanding, it put into consideration all the previous data points. So here you have, when you have 2 occurred, which is twice, then you have 3, you have 5.33. So we keep on doing that to this point. That is the example of expanding rolling average. So we quickly take a look at this quiz just to keep us going. Sorry, I have had a lot of time. And hello, can you guys hear me clearly? Please, Sumana, can they hear me? Hello.
Okay, Joseph, we can hear you fine and see the presentation fine too. I think we're all good. Thank you for checking though.
So time series forecasting, everything we've been learning for the past period of time is definitely taking us to this point, time series forecasting. How do we predict? How do we be able to tell people that, okay, we are sure of this is what the future holds? Sometimes it looks as if we're lying, other times it looks as if we're telling the truth, but this time around, we're making use of numbers. So numbers definitely should guide us in the right path, but with some level of accuracy. So for time series forecasting, an overview. Time series forecasting is the use of model to predict future values based on previous observations. So we already understood that. So we are just saying, okay, this is what it is, a black man. So the chances that your son will be a black, that is just what we are doing with time. Gathering all the previous observations, the past observations, understanding them, we can predict future values. Basically, that is what it is. Then we have the types of these time series forecasting models, which starts from simple moving average to standard or exponential moving average, autoregression, polynomial regression, and of course we'll talk about ARIMA, which is autoregression integrated moving average. So the simple moving average is actually the basic way of finding your mean that you all are, or we all are used to. So for instance, what you see here, we just pick these first three data, sum them together, divide it by the number of times they occur, which is 3. And then we have the next feature, which is 682.67. And if we want to consider the third column here, we'll 6, because 6 data points, add them together and find very friendly. We will look at the data is the one on the red from this indicator, and the predicted one are what you see here. This is the prediction for 3 weeks, and this is the prediction for 6 weeks. And you see, it doesn't really correlate in any way. It does.
Hey Joseph, sorry to keep interrupting you, but it seems like the audio is going in and out. Usually when you turn off the video, the audio quality improves. Maybe you could try that out.
Yeah. Hello, you said?
So Joseph, your audio is going like in and out.
Smart? Okay.
So can you turn off the video? Usually that improves the audio quality. I think that will help.
All right.
Okay. Thank you. Perfect. Thank you. Right. This is way better. Thank you.
You're welcome. So I hope this is okay. I hope that you can hear me clearly. So we have this red visualization here, and you can see that this doesn't correlate much with what we have for the third week and the 6-week prediction. So we have to find a way to improve that, and that drags us into exponential moving average. So okay. So the exponential moving average actually helps us because it tries to put into consideration the average of the raw observation in the original time series data. But meanwhile, it doesn't just take the average, it tries to put some things into consideration, which is the weight of the data points. So, and it also picks the most recent data points and try to find the average as it keeps progressing. So that's basically what what it does. It just sum and also most previous frequent data points, sum them together and take the average for the prediction. So that is what the exponential moving average does for us. Okay, please, if you can't hear me, just indicate, let me know. I don't know why I have to face this challenge this evening, but it seems to be fun so far. So let's talk about the linear or polynomial regression. The regression analysis in which the relationship between the independent variable x and the dependent variable y is modeled as nth degree polynomial. So for a linear regression, we just have this simple mathematical equation here, where you have the dependent variable and the independent variable x with all
Hey everyone, seems like we're facing some technical difficulties again. Thank you for being patient till now, and I really appreciate you being patient over the next few minutes too. Seems like Joseph is going in and out. He should be joining us soon, so please do be patient. We should be right back. And one more thing I want to mention is today's session might go a little over since Funke's session on implementing them is coming up too. So the session I expect to run over by about 15 to 30 minutes at max. If you do not have time to attend it, no worries. We will still be recording it and you can have a look on Slack once the recording is uploaded. Usually it should be uploaded by mid next week. So thanks again for being patient. We should be right back. And yes, we will start again from the time series forecasting whenever the speaker is back so that we can cover all the main concepts from scratch. So thank you again for being patient. We should be right back.
back. Okay. Okay. Approaches. Yeah,
Joseph, thank you for
yeah.
joining us again. Can you please go over time series forecasting again from slide 41? The participants were interested in hearing about it again. And it's okay if we run over, so you can go at your own pace.
Okay, from slide 41.
Yes.
Oh, okay,
Perfect. Thank you.
okay. Yeah, you're welcome. All right, thank you everyone for your patience, and I'm sorry for the inconsistency. Maybe I think I'm behaving like a non-stationary data. So, okay, for the time series data forecasting, basically what we intend to do is to take the previous observations or the data collected for the previous um, records and just put them together and try to forecast or predict the new data that we expect. But the problem is not doing this. The problem is how do we handle accuracy, and that is what calls for the several methods or approaches that we had in this. So we'll start with the simple moving average, and here basically what we do is you can see we created a new feature. We have the 3-week and the 6-week, and why we call it 3-week is because we pick 3 data points and sum them together. We pick three data points, sum them together to generate this new data point, and this is our prediction. For the 6-week, we pick 6 data
Joseph,
points.
sorry
Yeah,
to interrupt you again. I think you're sharing your
no problem.
screen. We're not able to see the screen that you would like to share.
Okay.
There we go. It's
Okay.
perfect now.
All right. Sorry, guys. Okay. I think we are having a great day today, obviously. So we just pick these 3 data points and we pick the average to generate. We have a feature, which is the 3-week feature that we generate, and the 6-week feature, and we are just trying to predict the data points in each of those features. And what we basically do is that we add these 3 data points together to predict the next data point for the 3-week feature. But for the 6-week feature, we add 6 data points together. So we add 6 data points together from 1 to 6, then divide it by 6 and have this prediction. But then it looks awesome until we visualize it and we realize that it actually performs very poor. So with this, you cannot tell someone that you are able to predict in 3 weeks what will be the demand, or in 6 weeks what will be the demand with this poor accuracy. And of course, most people will not like that, most especially if they pay you to do the job for them. So they want you to give them something perfect. That takes us to the next type. This is just a basic way of doing it, but we have more advanced way of handling it, and we are going to take time to look at that. So we have the exponential moving average, and what it does is that it tries to give concern or give consideration to the most frequent data points, and what it just takes the average as it moves, as it keeps progressing. It takes the average of the most frequent ones to predict the next one. So that is what we found under the exponential moving average. This takes us further to the autoregression. Here you can have it 2 ways, like simple versus the polynomial regression. Taking a look at this example, you can see that simple is actually lovely, but it doesn't do the work. From here, you see a simple mathematical equation for a linear equation or a linear equation, where you have the dependent variable and the independent variable, and these BO and B1 are the constants that you have around there. But what we notice here is that the feature is the module is unable to fit the data point. So by the time we do that with a polynomial module, you can see that it fits the data points better. So that is why we have to consider these different models. We have the easy easy way just to give us the idea, the concept of what we're talking about. But then by the time perfect, or will I say best accuracy becomes something of importance to us, we start considering advanced models to utilize. So that is that for the time series forecasting, and we are going to take a look at advanced approaches for time series forecasting. And here we have the naive approach, and we have the Horst linear trend, autoregressive moving average, and the rest. So we are going to take a look at them one after the other just to get idea what they are meant for and how we can use them. Okay. So while the naive approach is forecasting technique which assumes the future expected point is equal to the last observed point. Taking a look at this equation, I think that is simply what we are talking about. This is the present point that was observed, and this is the future. So we are saying, okay, the future is equal to the present. If you look at this chart here, you realize that the mean of this area is also the mean of the yellow colored area, taking a look at the amplitude from here. So that's what the naive approach is telling us. Of course, it has its own shortcoming. For an inconsistent trend, you cannot use this because it will be very wrong. I believe at this point you understand what inconsistent trend is. I mean stochastic trend. So you cannot use naive approach, of course, because of the inconsistency of the time series data. So we have the Horst linear trend method. What the Horst linear trend method does is that it tries to take the trend and seasonality into account or into observation. So in this case, if you look at this chart, you can see that at a point, the signal started increasing. So the prediction as well started increasing. It tries to take the trend into consideration as well as the seasonality. So that is what Horst's approach is all about. Basically, that is what it is. Though if we go deeper into it, you see lots of mathematics. And of course, if you want to do that with equation, with sklearn or other libraries, it will be easy, but the mathematics behind it, trust me, you don't want to see it now. So the main thing is for me to share the concept or the idea behind this with you. So we have the autoregression moving average. What this does is that it basically tries to pick two polynomial. It tries to take autoregression and also take moving average to form a prediction. You may say this doesn't sound nice. The thing is this approach is actually using two models. The moving average model and the autoregression model is trying to use them in parallel to make prediction. However, this doesn't sound great, though it is most important or relevant for stochastic processes where you have inconsistent data or signals. So it is easier for you to use those two approaches, applying them in parallel to the signal to make prediction. But then, okay. So this gives birth to another form of approach, which is the autoregression integrated moving average. In that stage, you have the autoregression and the moving average fused together to make prediction, which is way more better than trying to use the two models in parallel. So then we have the seasonal autoregressive integrated moving average. And in this, what we are putting into consideration is not different from the previous one. It's not different from ARIMA or the other ones. The only thing we are concerned about is the seasonality. In this case, we are putting seasonality into concern. So sometimes when you have data, for instance, like temperature data that has seasonality in it, and you want to make prediction, so you may have to consider this. And one other thing with this type of data set is that you may have to do a transform for you to be able to apply seasonal autoregressive integrated moving average. If not, it may not perform best the way you like it. So putting those seasonality into consideration, you can see that it performs better from our chart here. You can see the train and the test and the ARIMA itself, they seems to be very close, though there are errors in the lags. And the lags is what? The lags is basically the present observation subtracted from the previous observation, rather subtracted from the present observation. Those are the lags, and you can experience the lag between the test and the ARIMA module prediction on this chart you see here. So we'll now talk about vector autoregression. This method models the next step in each time series using autoregression model. But then what it does is trying to model two signals or more signals in parallel at a time. That is what the vector autoregression does. In fact, that is why you see the word vector in the name. You have two or more signals being modeled at the same time. So, and that gives us also, as we draw closer, we also have the vector autoregression moving average. Like we've talked about autoregression moving average, trying to apply two different modules, autoregression and moving average module. We'll try to use the two of them in parallel on a particular signal. Now, what in a situation that we intend to use those two modules in parallel with several signals, then you have the vector autoregression moving average. And of course, it makes our prediction better compared to what we have before. So, of course, one of the weaknesses is that it doesn't perform well with trend or seasonal data sets. So in such a case, you have to do a transform for the data set before you apply this method. So far we've been able to cover time series data and categories of time series data, such as stationary and non-stationary data. We also covered different time series, of which we are talking about observations. We talked about lag and how it has impact in data sets. And we also talked about seasonality and type of seasonality, which is basically seasonality repetitive short time cycle in the series. So, and how we can handle such. And also we talked about the lag features, which is under difference time. We talked about trend. We talk about trend in time series and type of trend in time series, such as deterministic, stochastic, global, local trends, and their impact and so on. So we talked about feature engineering in time series data, where we look at how we can perform feature engineering in date, in time related, in lag features, and also in windows, window intervals, or so on. So creating new features from existing feature. So we talked about time series forecasting. Yeah, naive approach, Hall's linear trend method, the ARIMA, and of course we talked about ARIMA and the vector autoregression and the vector autoregression moving average. So those are the things we've talked about so far. Funke will be taking us on the Collab project. Thank you very much for your time. And I'm sorry for the inconsistencies that you experienced earlier. Thank you all. Okay.
Hello, everyone. I hope you can hear me. Hello, everyone. I think I'm losing signal.
Hi.
Okay.
I can hear you. Yeah.
Okay, sorry about that. Can you see my screen?
Yes, I can see your screen.
Do we want to have a 1-2 minute break to grab water or drink, and I'll start sharing after that. Thank you so much.
Okay.
Oh my. Okay. This is interesting. Okay. Let me start sharing my video. Can you all see me? Give me a thumbs up, or and I'll be presenting soon. I'm looking for something. Sorry about that. Having technical difficulty here. Okay, let's just get this. Okay. So thank you, Joseph, for the presentation. for teaching us the intuition behind time series data and the concept behind different forecast approaches and model. Now that we're all done learning the concept behind time series data, let us get our hands dirty and try out some real data set. The code can be found at the link on this slide. One of our panelists will also share the link in the chat. Kindly open up in a new tab and feel free to follow along with me. I'll spend some time to walk you through how to open that in Google, and open the code from GitHub in Google Collabs and create your own. I believe we already have our the link has been sent to us, so I will go over this quickly. I'm sorry for the technical difficulty. I'm just making sure that everybody's hearing me loud and clear. Okay, so next we want to make a copy of this of the Google Collabs. Hyperlink has been shared with you. Quickly click on that. Go to Google and type in Google Collabs, and that will take you to this site. So click on GitHub, and you can paste that that link. Oops, I guess I didn't click on that. Okay, the link that was shared on the. That's it. Sorry about that. Seems to be a fun day today. Okay. So I'll go to Google Colab, click on the first link, and then go to GitHub and paste the hyperlink. Enter. Search for the Python notebook, which is the fifth one here. So you have it here. What next that you need to do? You need to make a copy of your own note in your drive. So you click on the file here. No, sorry. You click on the I'm trying to get to the files. You click on the files. Save a copy on your drive by clicking on Save a Copy. That way it will open to a new tab for you. And simply click Open a New Tab. So now that you have a copy of the time series, let's get started. Today we have learned about time series forecasting, and now it's been different forecasting approaches, like Joseph has helped us with that. So I'll quickly go over the note here. So the description of the problem is that we're trying to build models to forecast the number of passengers on the airline. Basically, what we need to do in this case is that the objective here is that we want to extract information from the historical series and use that to predict the behavior of same series based on the past pattern. We also we have a note here, but I wouldn't want to go over it. There's no need, but you can always go over that at your own time. It's just about all the things that Joseph have explained to us. So it has the application, where it's been applied, the components, the trend, the seasonality, the regularity, and the model. Now we get into the data loading aspect of it, the data set. What do we need to do? So the data set we will be using today is a univariate time series listing the number of passengers boarding aircraft per month from 1949 to 1960. That's about over 12 years period. The data set can be downloaded from Google, from Kaggle. And so you need to click on this hyperlink, and then I'll take you through how to copy that into your Google, I keep saying Google, into your Collab note. So when you get here, click on download. There are two ways. You can either click on download, or there you can go down to the, there's another aspect here, which is the data explorer. You click on download. So when you click on download, it downloads it to your system. Okay. I guess I've wiped my memory, but it downloads it to your system anyway. So you're able to download that data into your folder. I must have deleted and I have to remember the password. So it downloads it to your folder. Mostly it will download it to your download folder. You probably have to unzip that data and then save it to a place that you remember, that you know you remember, and you can really pick up that data. So in your Google Colab, you want to click on File. I have already uploaded this. I've already uploaded this, and so you click on File, and then you go to the upload to section storage here. When you click on that, it will ask you where it will pop up. So you have this airline passenger. Please load it. I've done that before. I'm just really doing that again. Next, let me quickly go over this. And we should also remember that this will, the uploaded file will be deleted after the runtime is recycled. So yeah, we're ready to do our coding. Okay, so if you look at this part, it says content slash airpassenger.csv. By putting in the PWD, it's just giving you the path to the current directory. If you are seeing it here, that means you have the correct path anyway. But if you click on that, it's going to give you, if you enter rather, it's going to give you the link, the path to the directory, and IS will list the files that are in that directory. And we are seeing sample data, that means you're there. So the next step is that we will import the libraries, the necessary libraries that we need for to do our time series analysis. So we will import, we are importing pandas, which is a data analysis library. We also have NumPy for numerical work. We also have the import square root. This will be used later when we're doing evaluation of our model, just to get a mathematical. You need the time. You need to import the datetime. The seaborn and the matplotlib are used for plotting our graphs, and the inline one will help us with for it to show on the screen. Anyway, here we define the size of our images pictures. So here we are loading the data as a data frame. So we are calling on PD read the CSV, and we're passing the data into it, and we're assigning it to a variable called airline. Now we're done with our loading. We can go into data exploration. Yeah, for us to understand the data and its features and make sense out of it, probably need to first we probably need to do some airline shape on all the rest things. But before I get there, there's something that we all know as a data scientist, like when we have data, it's very important for us to be able to explore the data, to understand what's in the data, so that we could use, we could understand the features of the data, and we'll be able to plot out the graphs in it, and that will help us in our modeling. So here, we are printing the numbers of and columns of the data set. We're using the airline.shape, and also we are printing the head. So there are 144 rows and 2 columns. Next, we could see how it's been printed, and then I also tried to print the airline detail that just shows the last 5 rows. Next, we're doing the airline.info. This is a type of, this helps us to print the index and the data type. And the memory information. So we could see here that it's telling us that the column month is object, and the passenger is an integer. So right now we look at the null-nil count, which we're checking the null to see if there are any rows that are having any n in it. Right now there isn't. So this is a great news for us. And so although we don't usually get such type of data set, this is a simple one, I would think. And so in time series, if we have to deal with the null data set that has a null in it, we need to make sure that there are no nulls in the data set. And if there are, we need to replace them with either 0 or average or preceding or succeeding number. So replacing is actually preferred choice by dropping, or so that we have continuity. And we could also observe that in the month column is string, because I said it's object. So we'll need to change this to date time. Rather than just having numbers that we have here, 0, 1, we want to be, that would help us with our modeling. That would make it easier on us. And so here we are renaming the columns from month to date. And I'll give you, sometimes you don't need to do this, but because we're going to do something else later on, that's why I'm changing it to date. And then you I'm changing the passengers to number of passenger, because it will not allow me to use the dot function. So Next, we are converting the data, the date that we have named here into the date column rather, from string to a date time, as I mentioned earlier. So what we are doing here is that we are passing we are passing the date column into the total date time, and so that will change that will help us to that will change the data type object to date time, and then after we could do our indexing later. Next, now that we have the data column in date time, we want to extract the month, just like Joseph mentioned. We want to do some feature engineering or selection, and so here we want to extract the month and the year and create a new month, new year column. From the dates column, we have the date all together. Here, it's going to give you, so the way I use the DT function to do that, DT month, DT.month and DT.year, and you have the month column, the new column month as one in numbers, rather than just the way it is. It's been separated anyway. And then you have the year column. So this was the reason I changed this from, because I wanted to have a column named month, so I changed the initial month column to date. So we're converting the month to column month abbreviation. What we have here initially is just 1, 2, 3. We want to have it in the regular January, February month. So we're applying, we're using the apply lambda function to it, and that will help us to convert that to January, February, and all the. And next, we are setting our date time as a column. We are indexing our date time. We can see now that it's moved. The way you see it here is different from here, so it's now an index as dates. So here we are summarizing the. We are giving a summary of the airline. What are the counts? The mean, the standard deviation, the minimum, the maximum, the quartiles. And so we could see that we have, of course, we have 144 rows of data. It tells, we know the mean is 280 and the maximum is 266 and the minimum is 105. So next we go to the time series steps. So we have visualized all these. We've not even drawn the plot, but I want you to see the visualization first. And so there are some steps that we're going to follow. And I found this visual very interesting. Maybe at least it will help you with the memory, remembering all of the steps. So the first steps we'll be going through is the visualize the time series. Second is stationarize the series. Then we'll plot the ACF and the PACF. We'll go through that later, what it means. We'll build the ARIMA model, or build our models, and make prediction or forecast. So going into the first step, which is the visualize the time series step. Here we are plotting data. We having an histogram of the data using the airline number of passenger.hist. And we could see the display of it. Further, we could use another one, which is the seaborne version that will give us a distribution, density distribution of this graph. Here is the density distribution. And from here, we could see that that the density plot shows that it's not a normal distribution, it's not balanced, as we could see. It's one-sided one way. If it's balanced, it should come down this way. Of course, this data is going to the next. So let's go to the next one. Here we are plotting the series. So we have the data, 144 rows of data, and here we are plotting the series. We're seeing how it is. Before I get into it, I know Joseph taught us what non-stationary is and what stationary time series is. Who can tell us if this is a stationary series or non-stationary? You can put your answer in the chat. I'll be waiting to see that. I'm saying some people say stationary, some people say non, something. Okay. All right. Okay. Some say it's non-stationary, some say stationary. Well, well, I would like to tell you that, well, this is not stationary. Why? Because the data, the series is trending, as we mentioned, and then we could see that the variation of the variance in magnitude between when we are in 1950, for example, to when we are in 1960, it's the magnitude is different, so it's not stationary. So thank you for your answer. I really I really appreciate that. And then so reviewing the plot, we can tell that it's obviously trending upwards, and there is seasonality component in it. As you can see, those patterns, those patterns that you see are the seasonalities. You can see from a particular time, you keep seeing the repeated pattern. So those are the seasonality in it. And from here, we notice that it starts like 12 months, less than 12 months. And more so, as I said, this is not stationary. And this could happen, you could see that there is a peak sometime in a particular time, and then it falls, it drops, and then it goes up again, it drops. So let's just draw another, let's take a closer look at the pattern. From 1952 to 1954. Here is another plot. So I use the range to get that. So it gives you the plot. We can see that there is this upwards trend, then it drops, and then it goes at very high again, and then it drops. So that's the pattern in the series. Obviously, as I said initially, there is seasonality in it, a repeated pattern, and the number of, and we also see that the number of passengers increases over time. And also, particularly, there is this pattern between July and August, where we have that peak. And this could also be to the season and time. It could be a holiday period. It could be particularly time that most people are on vacation, and of course the summer is ending, and the summertime, and everybody wants to enjoy it. So there's a lot of traveling occurring, and then it's also and people want to by the time it's dropping, perhaps everybody's going back to their real work. Now time of play time is over. So next, we'll take a look at the stacked annual plot to observe the seasonality. Here we have rearranged the time series to observe the seasonality using the pandas pivot table, which takes the data frame itself, and the value will be the number of passengers. And the column we want is that we want it to be, the column to be year, and it will be indexed by month. So our columns will be here, the number of the years, and we're having a month. So it outputs it this way for us. But we know that January, February, March is what we have. We usually have is not in this order. So the next step is to change it to the order that we want, and which is the January, February, March. So we are trying to reindex it into what we want, which is the January, February, March. So, and then this is a good, the other part of it, it gives it the colors that you see in here, the green colors. Next, we're also plotting the stack. We have a nano stack plot to understand the pattern, and we could see that it's almost similar. There is always a peak at this July, August time. It follows the same sequence. That means there is seasonality in it. It's just a different way of showing the information so that we get, we understand what we're saying. Another way, we also reorganize and transform the column rows in this way, because I want to show it in a box plots. And so it takes using the pivot table again, and this time around the value will be of course the data frame. It is the airline, the values in 4 is the number of passengers. The column right now will be the month, and it's indexed back to here. And so for that, to plot the box plot, this is a particular type of plot that will be able to tell us if we have outliers in our data. And right now there is no outlier. If there is outlier, you'll be seeing a sort of dots somewhere far away from everywhere, because this is supposed to be the minimum, the maximum, and then the 25%, the median, and the 75% quarters. And here, but if you have a outlier, you'll be seeing a dot so far away from those range. But right now we don't have it's good, we don't have no outlier in this. And August, again, of course we see that the July and August are peak months. And so also the variance value are much higher when you compare it with the rest of the other months. Another quick comparison that I also did is the mean and variance over time. As I mentioned the other time, I was trying to show you using my mouse, but here we will do it in form of calculation. So here I'm splitting the data set into 2 groups. We want to calculate the mean and the variance of each group. So, so the mean and the variance here, actually we're doing the standard deviation here, which is getting the data into the original value. The variance would be like the squared version. So, so anyway, so I'm printing this out. Mean 1 is 182. Mean 2 is 3. I mean the mean for the second half is 377. You can see that there is it's not the same thing. It's not constant. That means it's increasing. And same thing goes for the standard deviation. One here is 47, and the second deviation, standard deviation is 86. So clearly we can see that the time series is not stationary. Next, here I'm just dropping all those columns that I've added to it so that I can start my my analysis. I can continue with my analysis. Here we are. I split the time series data into train and test. Of course, we want to. We're doing machine learning. We need to split our data into train and test so that we could evaluate that our model is performing well. So here I've split the data into close to 70. I wanted like 70 to 30, but then I find a way of splitting it so that I have a complete month, a complete year, rather than having a break in between. And so we have the size of the trained data is 96, and that of the test data is 48. Here I'm printing out the head of the train and the head of the tests. We could see that it starts from 1949 for the train, and it starts from 1957 for the test data. Next, we're going to plot. We just see, this is just a visual of what we have split out, the train and the test data. So here is the test, here is the train rather, and here is the test data. So that takes us to the second step. We have done visualization of the data, and now we could go to the second step. And it is important for us to stationarize our data because it will help us in making a better focus. So there are a number of steps that we could follow in stationarizing the time series. There's another one, maybe I didn't include here, which is the trending. But we could use these ones, these two. We could difference the data to make data stationary on the mean, which means that we are removing the upward trend that we are seeing. And then we could also do the log transform. We could do a log transform of the data to make the stationary, to make the data stationary on the variance. Next, but before we do the before we stationize the series, I think we should just quickly take a look at, on the establish the base level forecast. For most base level forecasts do not require data stationarity. So we'll probably not be stationaring any data there. That's why I said we should wait a little. We just do the forecast for the base level. And so yeah, let's take a look at some of the models that that Joseph has explained to us. We mentioned the naive method, and these are simple estimation technique. It assumes the predicted value at a time t-1 to be actual value of the variable or of the, well, that's a variable of time t1 or at the rolling mean of the series. What we're saying here is that if there is a time t1, we want a value for t1, the present time. So we are using our past data at t-1, like yesterday. We are today. We want to know what today is. We are using our past data t-1. And sometimes you could take it the other way. I saw a question in the chat, somebody asking, do you use t-1 or or t+1? It depends on where you're starting from. Someone could be looking at it that, okay, today is my present, which is t, and I'm using t-1 as my past data. Or some could say, okay, my t-1, my t+1 will be my future, but I'm using, of course, I'm using t, time t as my present, and my t+1 is a future. So you can want to, sometimes you might say, okay, I want to know the future based on the present time t, or I want to predict my current day, which would be tomorrow. For somebody that's talking about yesterday, will be t-1 using the past data to predict the future, which is today. The future, that's funny. Anyway, so we set the predicted value to present time equal to the value at previous time. So here I'm just trying to show you what we are doing. What I'm doing here will be much easier to tell you in this printout. So for the naive forecast, we have the current time t, current number of passenger t, and then t minus 1 here says the future. Maybe I mix it up here. Anyway, what I'm trying to say here is that t, the future. Okay, so what we're doing here is that we're taking the previous data of February. We are using that to become our future, which is 301. I probably would have mixed this up here, but so if we say t is the current one here, and then the future would be t plus 1. But if we say t is the past, okay, so I'm not mixing it, we say the same thing. Okay, so if we say this is the past, if we use t as a past here, as a past year, then probably this is our future. Still mixed up anyway. Anyway, the idea is that this is our future, this is our current, and this is the future. So we could see that we are using the 301 here, and the next day, the future will be 301. In March is 356, and then the future for April will be 356. That's just the idea. And so here we have a plot of how it goes from the orange is the test data, and the trend data is blue, and the trend data is blue. The orange is almost the same thing as what we had initially, but the future, what we are predicting as the naive forecast is the green one. We could see that it's just shift. Another way is that of doing it is okay. Before we get to another way, here we are calculating the Rmse to know how our model is doing. So we do that by taking the square root of the test and the forecast, and then we get the 48. In the basic technique, the error of any other model that we will be predicting, that will be building in the future, will have to be much smaller than this. This is just the basic technique. So there are different smoothing methods. We'll go over that. The smoothing technique, I think Joseph already gone through this. I don't know whether I should. Let me just speak to it. Anyway, smoothing method work as weight average. The forecasts have been weighted average of past observation, and the weight can be uniform. When it's uniform, we say it's the moving average, and then when it's exponential, then we'll be talking about the simple exponential one, and other ones that comes after it. And so, but the more advanced method will be using the seasonal and the trend component. So going to the moving average, I will quickly go because I know we have our time is going. So the simple moving average, we forecast the next value in the time series based on the average of a fixed number of previous value. So here, that is the rolling average that Joseph would have explained to us. So you see that the first 3 values of test data are missing, because the January, February, and the March, they're missing because we are using those data, we are averaging it together and making it the next average for the for April. And then the same applies to the rest of the data. and we don't have data for January. We couldn't do the rolling average for January, February, March because we have null there. It doesn't even exist. So we have dropped those aspect of it. So we're just seeing the February, the April, May, and the rest of the month, rest of the year. Anyway, so moving forward, here is the diagram or graph that shows the rolling average, how it shifts. And also I have the accuracy of the model here. Here it's 69.52 compared to 48 that we had initially. So you can see that the more we for the moving average, it's more. So here, as I said, we use the lag 3. We could increase the lag. And so in the next one, I'm showing you what if we increase the lag to like we have more lag, we have 6. So what this code is showing is that we are taking 6, we're starting at 6, we are increasing at 6 interval, step of 6, up to 20. So we want to do the rolling average. If we say it's 6 here, and we take the mean and we shift. So that's the way to do that. And then we drop the null values, and here we're just plotting the data, the test data, the train data, the test data, and the rolling mean. So when you plot this for the observation, this is the one for 6 observation, this is the one for 12 observation, and the 18 observation. And this is what we see. We can see that it gets smoother and smoother. And next we do the root mean square error. And here we have 73.99. We can see that the prediction are getting weaker as we increase the number of observations. So going to the next smoothing method that we have is the simple exponential smoothing that uses weight. So the forecasts are weight of previous level and the current observation. So where the weight decreases exponentially as the observation comes from the past. So the ones that have the past gets the weight that is given to them are less. So the smoothing level that is used is denoted as alpha. Here is the introduced into the stack model. Unlike in the past that we've done some machine learning algorithm or use of models, we've used the scikit-learn. Here we'll be using the stack model. And so from the stack model TSA API, we import the exponential smoothing. And I'll quickly run this through. So what we do is that we make an instance of the model, or create a model using the train data set, and then we fit the model, and then we'll do a forecast. Yeah, I've done the one for alpha equals to 0.2 and alpha equals to 0.6, and we plot the graph. So here's what we have. And then the root mean square error is 119 here. We could deplete it to it that it could be due to some the data that we have. And also we go to the hot linear trend model. This is an extension of the simple exponential smoothing to allow forecasting of data with trend. And the smoothing level, it uses 2 levels here, alpha and beta. So the smoothing level is 0.2 here, and it has a what is called the smoothing slope of 0.1. And here we are plotting the graph we could see the slope. This is how it presents it to us. And the Rmse for that is 66. Again, we move into the Horst Winter method. Here, this model takes into account the trend and or seasonality. So it uses other like the levels and the trend and seasonality component ST, and also uses the smoothing parameter alpha, beta, and gamma. Anyway, those ones are not really shown here. It's typically is inside, is more into the model itself, but we're showing it that it has a seasonality of 12, and we say it's multiplicative because it's increasing. It's increasing, steadily increasing. If it were just on the same level, it's not increasing so much, but you see the increase, we might say that's addictive. I didn't go through the note I have. That I just mentioned the categories here, and where we could see the Rmse error, it's 42. So if we compare that to the very first one that we had initially, which is the naive, we say it's 48. We had 69 for moving average. For simple exponential smoothing, we have 119, and the hot linear for 66. And we could tell that from the above result that clearly the Rmse of the hot winter method is the least, and so it's the best model for smoothing. Okay, so let's go back to our visualization. I'll just pass through this. It's just what we've seen. We already know that there is trend in it. So for us to be able to build a model, we need to stationarize this data set. And so that means our mean, our variance will remain constant over time. And our auto variance does not depend on time. So here are the checks that we typically will use. So there are two statistical tests to test stationarity. We have the rolling statistic and the statistical test. That's interesting. So the rolling statistic, in the rolling statistic, we tend to plot and review the rolling statistic, I mean the rolling average and the standard deviation, just to see. We'll plot the graph. And the second piece of it is the statistical test, which uses the augmented Decomposition test. So here it's going to be is a confirmatory evidence that the time series is stationary, non-stationary. That's where we know whether it's stationary or non-stationary. It uses this hypothesis or null hypothesis that there is a root, there's a unit root. I will be getting into the details of that. That it's non-stationary. That means there's some time-dependent structure in it, and when it's so when there is root, a root in it, there is non-stationary. And then when we also use the other hypothesis, the alternate hypothesis H1, we reject the null hypothesis, meaning that the time series does not have a unit root in it and it's stationary. Let's just get the fact that it's stationary at that point. So when you have null hypothesis, it's non-stationary, and when it's alternate hypothesis, it is stationary. So we reject the non-stationary and then we use the null hypothesis. So in that test, we'll have the test statistic will be less than the critical value. There is a critical value that we're supposed to use. So if our test statistics tells us that is greater, if our test statistic is greater, then we know that it's non-stationary. But if it's less than the critical value, then it is stationary. Anyway, let's go to So here is just a test stationary function that combines those two, the rolling statistic and the test stationarity, the statistical stationary test. So it's a function of, so you have the rolling statistic here, and we plot the mean and the standard deviation. And we have the statistical test, which use the augmented Decomposition test. So here, what we are doing is that we're calling on, we're passing the time series data into the augmented Decomposition, and we assign that to a variable ADF test, and we're having our output. Here we just want to so we're having our output, and here we just want to print the output that is between 0 and 3. That means so 4 is not included. We need four things to be printed out from 0, 1, 2, and 3. So here's an example of what is happening with the rolling. I don't think I should go through this because we've done the rolling statistic itself. So here we are using a rolling statistic of 12, and so you won't see anything because it's using the average of the first four, the first one to do the mean of the next one here, same as the rolling STD here, the standard deviation. And here is when we call the function, the test stationarity that I mentioned up here. And then, so we assign the column, the column, the number of passengers to this variable, and then we'll pass that variable into the test statistic stationarity, and then we'll print it out. This is what it prints out for us. We could see this is the original data in blue, trending that we've seen before, and this is the rolling mean that we see with, this is for 12 window of 12, rolling mean for window of 12, and this is the black one is the standard deviation. We could see that it's trending. Of course, I don't want to go back to that. So the mean and value and the standard deviations are not constant, but they're varying. But the result of the Decomposition tells us that if we look at the test of the Decomposition here, we have 0.815, and then the critical value at 1% is about -3. 5% is -2, and 10% is -2. So this is way higher than the critical value. And so if that is the case, and also the p-value here is 0.99, and we could tell that this is not stationary. So we will fail to reject the null value, null hypothesis. We also have to note that we have option of either using the critical, some people use both, or using the critical value or the p-value to evaluate the result of the test. But I will just use the critical value here. And also the time series indicates there is an exponential growth, as I mentioned. And so in order to make this better, we will be doing the log transform, and that will help us to flatten the exponential to a linear relationship. And so there are also a variety techniques that we could use. I'll just go through that quickly. I've mentioned that we could do a log transform. Some could use, some use log transform, some use power transformation, or that are square root, cube root, to remove the unequal variance, as we saw in the graph. And then we could also, we could use the differentiating of the time series to address the trend component, the trending, the going higher and higher that we see there. And so we could use a simple moving average, we could use the exponential moving average, and we could use the previous value. Another method would be the seasonal decomposition. For the next series, let's try to use some techniques. First, we want to do the log transformation, and that will remove the unequal variance. And so we are assigning this to using the NP log, the numpy to do this. And that gives us, here we are plotting the output of the log. Remember, we have it, not sure how far that we go. Okay. What we have here, we have 0 to 600. But because we want to flatten it so that we don't have that big trend going up, or variance rather. So we don't have that variance that is between them, that you see the difference between here and from here to here. So we are trying to do that using the log. And now we have the numbers between, say, 4.5 to about 6.5. And so that way we could see that the variance has changed. They are more or less equal compared to the other one. So next, let's use the trend reduction technique that we've learned to stationarize the mean and the variance. So we either will be differencing, we'll be doing our differencing one using the moving average. Next, we use the exponential average, and then we do the previous using the previous value. Here we passed, we've gone through this. Let me move on a little bit quicker. So here is the plot using the simple moving average, which we have done. We could see that the unequal variance is removed, and the observation, we could observe that the increasing, we could observe an increasing trend still. So we need to remove the increasing trend. And that's when we do the differencing to remove the trend. So we have we initially transform our trend data and our test data into log using the log transformation. So we're going to subtract the moving average that we got up here from the trend log. And then we'll drop the null value and just print it out. I'm just showing you what the value is. And maybe in another step down in the code, I'll show you how we did this. So yeah, then we're passing it through the test stationarity to know whether it's stationary. So here is the plot. We have the original data in blue, the rolling mean in red, and the mean rolling standard deviation in black. And so we could see that the rolling mean and the standard deviation appears very slightly, though it's and it's much better than the original one that we had initially. And the test statistic is smaller here. So we have -1, the test statistic is -1 here. So it's smaller than, if we look at the 2.5, -2.5 is still is smaller. -2.9, it's smaller, and -2.2 is smaller. Anyway, this one is smaller than the 5% that we have. So the test statistic is smaller than the 5% that we have. Okay. And so we are confident that 95% of our trend is removed. And the p-value is also there. I don't want to really go into it, but then we know it's 0.32. So it's not stationary. It's not stationary. Yeah. So the next smoothing average that we have is the exponential weight moving average, where we use weights along with it. So it takes in the train log and use this function and with the exponential weight moving average function and with the mean. And here's what we have. Again, we can see that the unequal variance is removed, and we can observe, and we still observe an increasing trend as well. And so we are going to do a differencing. So the next step here is just doing a differencing from the mean of the exponential weight. We take that from the train set itself, the train log. And then we pass it through the test stationarity, and we could see what we have again. Here, the mean, the rolling mean seems to be also a little bit constant or still vary. We cannot be 100% constant, and so same for the rolling static STD, which is the standard deviation. So the result of the test statistic is minus 2.83, and the critical value for 1% is minus 3, which is much less. For minus 5 is minus 289. For minus 10 is for 10% rather is minus 2. So we could say that this the test statistic is smaller than 1% of the critical value, and so we are 99% confident that this data is stationary now. And so the thing with this is that this trend doesn't, they're good. We could say this one is very good though, but the problem here is that we've seen data with seasonality in it, and so this technique do not really work with a high seasonality. And so we'll try the next step, which is using the previous value of the data. So here we are using the previous value of the time series. We take a difference with a particular time log. This way we are trying to remove the trend as well as the seasonality too. Anyway, so here what I've done is to take a shift of the log data in the translog column, and shifting will just be taking the value in January and putting in February, just like what we have here, and then we do a difference. So when we do a difference, so this is the one I wanted to show you, just to show how this is working. So you have the log, the train log, you have the shift of the train log, and this is the difference. So what we did here is to take a difference of ignoring this one because it has no value in it. And so we are taking the difference of 7, we are taking this value, the shift value from the train value, and we are getting 0.052. Same goes for the rest of this. So we are taking the difference of the shift value from the log value. So which just means that we are taking the difference of the remember we are just shifting it down here, so that means we are taking the difference between this one and this one, the data here and the previous data. So I just brought this up so that we can see the illustration of how it's been different. And here we plot the graph, and we can see that here we have a difference. We have only difference it once, and it looks much better compared to what we've seen before. And here we drop the null value, and we plot the we pass the difference of the shift of the log to the test stationarity. And here we'll see there is no trend and the output is relatively flat. I'll go back. The output is relatively flat. The ADF test statistic is like a 10%. Let's see. So the test statistic is minus 2.667 here, and it's less than the 10% critical value. So we could say it's to some extent that 90% confident that our data, that the trend is removed. So now that we have stationarized the data with using one difference, so we call that an integral part of ARIMA. So there are 3 parts to ARIMA, which we'll get into: the AR, the autoregressive, the integral part, and the moving average. Do not confuse the moving average here that you have with the moving average that we've been talking about. It's not related. The moving average here is more of like error, not what we have been talking about. So do not mix them up. So somebody's asking that where is the 90% coming from? The 90% is coming from the fact that we have a critical value of, we could say that our data is less than this 10%. This 10% here, 2.67, is less than, if you look at it, don't look at it like in a positive way, you missed it. So minus 6.7 is less than minus 2.59. So if it's 10%, we are confident the 90% is from the 100 minus 10, and we can say that for that our data is 90%, the trend is removed rather. So I hope that answers your question. And then the other part is the seasonal decomposition. Here is another packaging stat model that will help us to remove, to separate the trend, the seasonal, and the residual. And so here we are passing our data, our train data, and we are giving it a frequency of 12 to the variable decomposition. And we have the trend, the seasonal, and the residual being stored doing the deposition, the trend to be the trend, and likewise the decomposition, the seasonal being the seasonal. So here we are plotting the graph. Here we have the seasonality. This is the original data that we've been looking at. And here it separates the trend, the seasonality, and the residual. And the residual is just what you take out of, when you take out the trend and the seasonality from this graph, you'll be left with this. That's what you're seeing. So it's more like noise in the system. So the trend is, you can see it's going up as we see, and we see the seasonality. This we have seen the pattern many times. So it's just separating them. And here is the noise. So the noise sometimes is referred to as irregularity. It's called noise. Sometimes it's called random. So the noise here does not really have a specific pattern. We could see it goes, we cannot really predict it. For seasonality, we could see what is there. Anyway, let's go to the next one. We now want to check for if the residual itself or the noise, random, some people call it, whether it's stationary or non-stationary. So we pass the residual into the train log as a variable, and then we pass that through the test stationarity just to run that through again. Through the test, I told you initially that the augmented Decomposition test is what we use to know indeed whether our data is stationary or not stationary. So we're passing this into this again. We could see here that our test statistic is -5, and critical value is 1, of 1% is -3. for 5% is -2, for 10% is minus 2.5. We could say, oh yeah, it's stationary though. The regularity, one would say that, oh, it's -5, is less than all the values of that. So at this point, it's stationary. But then the regularity doesn't really, the irregularity of the system is not stationary, though here, though the test statistic is telling us that it's 1%, is even 1% that is stationary. Anyway, so we go through the 3 parts of ARIMA before we get. I will quickly go through this. I know we've all been waiting. It's a long one. The ARIMA is divided into 3 parts: the ARIMA, the AR, the auto-regressive, the integrated, and the moving average. When we difference initially, we have the differential part, which is called the integral. We go back to our maths when we have our integration, and then we are asked to difference it, like when we have 2 raised to power, let's say 2, let me just give an example. And like we have 2x squared plus an x plus, let's just say plus x, 2x squared plus x, and then we difference, we lose the x, and then we will now have 2 times 2 becoming 4x. So there we are changing from 2x squared plus 1x to becoming 4x. So that's the difference. So that's so sometimes you see those words difference, integral, they look coming together, they work hand in hand. And then, so difference in here, subtract the time series from its lag series to extract the trend. And the ARIMA, so the auto-regressive extract the influence of the previous period on the current period. The moving average, we are extracting the influence of the previous period error term on the current error term. That's why I said don't mix this with the smoothing average. It's better to even say smoothing average rather than moving average. Sometimes those names are confusing. So here, the 3rd step is that we're going to go through the plot the auto correlation function. So here we are trying to identify the potential AR and the MA model in the residual. So the definition of, well, I would just say a good way to distinguish between a signal and a noise is the ACF, by finding the correlation between the series and its lagged value. And the another definition could be that is a correlation of the series with its own lag. If the series is significantly autocorrelated, the previous value of the series lag may be helpful in predicting the current value. And the partial autocorrelation factor, PACF, conveys similar information, but it's pure correlative of the series and its lag. So it's excluding the correlation contributing from the intermediate. What does that mean? When we have a series that is T -1, T -2, T -3, up to T -5, the autocorrelation is looking at the correlation with all of this. So it's a whole piece. But when you do the partial autocorrelation, is only checking the correlation between T1 that we mentioned, the T and the T -5, excluding those ones in between. So in order to create an ACF and PSCF plot, here is a function that we need to use. There are a couple of ways. Sometimes some are confusing, some are easy. So there is this first one I'm showing you. So we're passing the translog, the difference of the translog that is being shifted into ACF, and same to the PSCF function, and to get the plot. So we are plotting here, we're just plotting all of this. We are putting some lines in the graph for us to see where the cutoff is. We'll go down straight to this. In this one, it's easier. Sometimes some people say it's better to use this one when you have just one, whether it's the AR model or the PA or the MA model, but it's not good when you have both of them. But then let's just use this one. So from what we see here, what we are looking at is when the curve, this is a plot of the difference, the shift of the train data. And so the first time it drops at 0.0 is when that's where we want to mark. So at that point from here, it's very close to 2. We will see, well, I'm not seeing it clearly, but we will say it's very close to 2. Don't put my, we will say 1. And the same for the partial autocorrelation function, with the first time it cuts off, it's about 2 too. So I would say it's 2, and we already have a difference of D equals 1. So another method would be to use this method called, let me see, to use this method called, there are many ways, that's why I said there are many ways. So here, this one is a little bit confusing to me initially. What they are trying to do here is that when you see one of these lag, if it's above, this is the critical values also. If it's above this critical value, that's when those are the lags that you pick. But here it's even a little bit confusing. Perhaps this one is 2. We will say, well, it's close to it. Maybe it's 2. Then we'll look for the autocorrelation. It's almost similar. So it's not a little bit confusing. So I wouldn't use this for now. Sometimes it's much clearer depending on the data. And so another one that I found that even makes it clearer, using the simple method for the ARIMA that we are using now, since we have not gotten to the seasonal part of it, is using the stack model, the ARIMA order, importing the ARIMA order, select IC. So the IC, the IC here could be the IKK information criteria, which we'll get to later, and there's also the Berkshire information criteria. And so the main thing that you're looking for is looking for the minimum value for each model that you're trying to present. But from this this function, we could see that the best model it presented to us that the BIC minimum order will be 2-2. 2-2 meaning our P I'm not even sure if I've even explained that. Our P in the ARIMA is 2, and our Q is 2. So we can say the AR is 2, the MA is 2. I'll quickly go through that. Wow, this is a long one. Okay, so the ARIMA model here, here we are using those parameters that we have here as 2-2. So for the ARIMA model, we are using, we're trying to fit a model to find the P, the Q, the Q parameter. We already know the P, the D rather. So we have a function here that I'll quickly go through. So we are using the P for the AR model 2 and the difference 1. Now we're passing it through, we're creating an instance of a model, and then we'll fit it. Here we don't want the display out, that's why we have a -1. And so we're printing it out, and we're also getting the residual square error. So here, when we look at this, the residual error that we got from this says that is 0.95. And as we print just the tail, the reason I'm doing that is because we want to know how well our module is. And so I'll quickly run through this. By the time we get to the bottom piece, I'll explain more about what's happening here. So we are trying to get to the, we're trying to print out the plot, how well our model is doing. At the same time, we want to print out the root mean square error. So here we are using the date between 1957 to 1960 to do a prediction. For that, that's our test anyway. So we run this through, and we have the MSE to be 60. That means this is to evaluate our model for AR model. And next we go to the MA model. Here the P will be 0 in MA because the Q is the MA model. So initially we have the BIC to be 2, which means the Q is 2. So we are using the difference, and then we are using the 2. Somebody mentioned that the time series is so long. Sorry about that, but it's better we just go through this. And so here we're having okay, maybe I'll go quickly. So here we're having the Rmse displayed for the MA model, and we have it at 63. So for the AR model, it's like sorry, it's 60, and the MA model is 63. The time series model is quite large. This is just a simple aspect of it. So the ARIMA model here, we are adding, we are now fusing all the models together, the AR model, the MA model, and the integral part of it. And so we are going to plot what now we are putting we're passing all the parameters, the 2, 1, 2 into it. And we are getting our RSS is 0.693. I don't know if I even went through that. So the lower it is, the better anyway. So, but here, it's better here because I think we've been having 1.4, maybe, okay. We've been having like 0.9, and then we have for the MA for 0.8, and when we combine both together, we have the 0.9, which is much better. So here we're having the Rmse, which is the evaluation of our model, and which is 63.97. This is much better than what we had individually, 63.84. Anyway, let's go further. Oh, okay, that's why. Anyway, maybe it's because of the data. Yeah, we are printing the summary of the data. I'll quickly go down because we have more. And here we're printing, we're checking the accuracy of our model visually. We will see the forecast is what we have in blue, the orange is the original. And so we have the prediction and the reverse transformation. For us to get back to our original value, we want to because remember we did a log transformation, we differenced the data, and then we did a shift somehow. So for us to get back to, so now we're having the data that is not like the original value that we started with. So we want to go back to original value. So in doing that, we need to convert the fitted value into we need to convert the fitted value that we have, run some mathematics here. And so we'll pass this data into the, this is just to see what we have. So here we are going to do cumulative. We did a difference. So we are negating it. Now we are doing a cumulative sum. So when we do a cumulative sum, this is the output. And that's when we want to add that cumulative sum that we have here to our log. And so we convert the log difference value by adding the difference, start adding it back to each other, to what we had initially. And so we calculate it. So to get now, you remember we have log data. So we want to convert that to log data. We want to convert that to the original value. We took a log, we are now going to take an exponential value. And so this is the output that we have. And here we could forecast our data. So for the next 10 years, this is what we will forecast. And here is the, if we want to print it out, this is what we'll have. And for the forecast, the original value, this is what we'll have. Anyway, let me quickly get into the seasonal ARIMA. That will be the end of it. So the seasonal ARIMA has the 7 variables, 7 parameters. So we have the P, the D, the Q of the normal ARIMA, and then the seasonal ARIMA has one other one, which is the frequency added to it. So that's what I have here, you can read it. So we took a log of the original value, and here we go through, here we're just defining our P, our D, and Q parameters between 0 and 2. And then we generate a different combination for it. And then we generate a different combination for it, and then we select, for us to select the best model, we are passing, we're using the stats model API as SM. And then we are creating some variables to store our data. So we created 2 loops, one for the normal ARIMA, and then for second for the seasonal ARIMA. And then we create an instance of a model here. Next, we'll fit the model, and we'll pass the result, the output into result. And here we are comparing, we're storing some data into the result and comparing the best AIC, that's the archaic information criteria. So the best one will be output. So it runs through this many times. So we will have, so it runs through this and will give us the best, the one with the lowest value at the end. So which is minus 44. This could be 10. It will be too much for us to be doing it by ourselves. So for each of those combinations that we have, it fits a new model. It has different models. You can imagine we're talking of something of 0, combination of 7, combining 7 things. And so those values are put, and so the archaic information balances the model between goodness of fit and the number of parameters used. Anyway, this we could read over. And so we are fitting the model using this. So when you came out of this, the best model that was given to us is that our P is 1, difference is 0, our integral part is 0, and the moving average is MA is 1, same, and then the frequency is here. And so we fit this into the model. We have the model, we create an instance of that model. Now we want to fit it. The other one was just giving an idea, and then we fit this, and then we print it out. So here we are seeing the result of the diagnostics. What this means is that we could see here that our mean, our variance, this is the error. So it's all, the mean seems to be equal to 0. It's more or less not like the previous one that we had that was all over, we couldn't tell, but this one, everything seems to be, if it goes up, it comes down, if it goes up about the same time, so it's 0. So that means that we have a white noise now. And here we could see that initial histogram that was not well distributed is now has a normal distribution. And here we are fitting the data, and we can see that we have almost like a linear regression here fitted. And the other one that we couldn't really understand here, now we could see that the Collogram here is showing that immediately the next lag really cut off. And so here we need to validate the forecast. So here we are validating our forecast and passing this data into predict. And here we're getting the confidence interval. And here's a printout of it. And then we're plotting the forecast value with the historical data. Using different, I won't bore you with that, let me just go through this. And then we'll have the prints out here. We could see this is what we have as our train data, and this is what we have as our test data, and our predictions are in the our prediction are in the our prediction are in the orange color, and the confidence is the one that is in the grayish thing that we are seeing there. And here we have a printout of our predictions that we have. The next is we calculate the Rmse. Here we have a Rmse of 0.23 compared to all the ones we've been seeing, like 49 and all. Like the one we've been seeing for the AR model, which are far back here. Let me not go too far. Yeah, but you get the logic anyway. So it's much more. That means that this model really works for seasonal data. And so taking you back, we're almost done. Sorry for the long one. And so we are producing and visualizing the data here. And the next thing, we can see our forecast for the next 10 years. This is how it's going to present it to us. And so if we want our original, we want to get back to original, remember this is the log data. So just like I've explained before, we use the exponential, the NP and exponential function to get back to our log data. And then we'll have the original data. This is what we expect. So when we started, we have values between up to 622 as the data. And then we are predicting for the next 10 years, we are really going even into the 1,700 passengers in the future. So that concludes our time series. That concludes our time series, and I hope we enjoyed this. So in conclusion, we explored visualizing the time series. We checked for outliers, the missing values, and observed the trend. We reviewed the naive and the smoothing model. We make series stationary. We transform the data using the log and difference and check the stationarity. We plotted and examined the ACF and the PACF to determine the input. We use that input to estimate the model and select the P and the D and the Q and the AIC value. We also build and fit ARIMA family, the AR, the AML, the ARIMA, and the seasonal ARIMA. And then we calculate the Rmse. So from here, we also do this diagnostics of the model. So that concludes our here are some reference, and here are some homework. I believe we have that in the PowerPoint. So I'll quickly move to the PowerPoint. Okay. I don't think we're seeing a PowerPoint. Let me just go to this other side. Sorry about that. Let me share this one. So that concludes our, oh, this is a wrong one, sorry. So that concludes our thank you all for joining. I hope you enjoyed today's section. Sorry for the time, it took so long. Hopefully, we didn't take too much of your time this weekend to learn this concept. I believe it's something that we can use. It might be time consuming, but something that's excellent for us to use. We can use that to predict the future of many things that we do on a daily basis. So if you have questions regarding the content, do join us on the Slack channel. Post your questions to the Help Me channel. one of our panelists will share the link to join on the Slack. So we look forward to seeing you next week when Sneha and Rishika will be covering the we'll be covering neural network. So thank you so much for your time. So if you have any question, we can send that to the Slack channel. So sorry, today we have some technical difficulties, and we are happy that we're able to go through this together. Thank you for your time. Thank you all. I really appreciate it. Thank you for staying and hanging on even till the end.